So before we leave the subject of Bode plots, I'd like to do one more plot. This is kind of a tricky one because it's got complex zeros. Anytime that it has complex poles or complex zeros, if you've been reading along in Appendix E of your textbook, you'll note that they're a little more difficult than some of the other pieces. So what I'm going to do is I'm going to start out with this one. I'd like to change the way it looks a little bit. Obviously, this term here is how we recognize we're going to have some complex poles or zeros. Since it's in the denominator, we would have poles with this one. I'm going to multiply by kind of an odd factor here, 1 over 100, and then I'll maybe multiply also by 2. And I can't just do that. I've got to do that top and bottom, 1 over 100. And then times 2. So when I do that, of course I'm just multiplying by 1, kind of an odd looking one, but when I do that, you've got 25 divided by 50 turns out to be equal to what? 0.5 j omega, and then in the denominator I get 2 j omega plus 1. So I bring the 2 into there, and then this other one is where I bring the 100 in. It's going to have j omega squared. Let's see, j omega over 100 squared. Make sure I do that right. No, j omega over 10 squared. When I have 10 squared, yeah, then I get the 100, so I'm good there. Plus j omega over what, 25 plus 1. So I'm taking the, I'm multiplying the 1 over 100 times this one and the 2 times that one, which should be a fair game. So I get something like that. And then we're going to end up having to do quite a bit of work with this one. We've got a couple terms that the amplitude in decibels is going to be equal to 20 times the log of 0.5 j omega, and then I have to subtract off 20 times the log of 2 j omega plus 1, and then I have minus 20 log, and I've got this whole thing, j omega over 10 squared plus j omega over 25 plus 1. Okay, and this one's probably not too bad. That should just be a line like this, right? It's not going to have a corner. It'll just be a line like that. Then we could pick a couple points. What if we took a point, let's say omega is equal to 20. What would we come up with? If omega is equal to 20, I got half of that. So I've got the log of 10, which is 1. So 1 times 20 gives me 20, doesn't it? So our answer would be 20. So we're going to plot the point 20, 20. And what if omega was equal to, what was another one that I did, 2? So if omega is equal to 2, we put 2 in there, we get 1, we should have 0, shouldn't we? So I got a point that's 20, 20, and I got a point that is 2, 0. Then this one's going to do what? It's going to go and turn down. Where's the corner going to be on that one? Yeah, it looks like a half, doesn't it? Omega is equal to a half. It's going to turn down, and it'll drop at 20 decibels per decade. And then this one is where we're going to earn all of our money on this one. This is quite a bit more difficult. If you go to the web page, there's a couple of PDFs that talk about helping you to do this. Also, your author in Appendix E talks about this too. But basically, what this breaks down to is, if I look at this thing, I have a couple of terms that are always come out. I have this term that always comes out, what's in front of the squared. I have this term that comes out, and I have that term that comes out. And I can say that this 1 over 25, so I have 1 over 10, which is 0.1, and I have 1 over 25. Okay, and those have some fairly specific names. This one would be 1 over 25, I say, is 2 times zeta. So if I do this, it's kind of a lambda, but zeta. Two times zeta times tau. Okay, and the 0.1, this turns out to be equal to tau. Okay. So what this will actually be is where the center is. And then if I know what tau is, I've got 0.1, I can figure out what zeta is, right? I think zeta has a little more swoosh on the back side of it than I'm giving it. Okay. Because if I take this as 0.1, and I have 25, what does zeta have to be? Yeah, it should be divided by 0.1. Should be 1 over 5, right? Because this is 0.1. So 1 over 5 gives me 0.2? Yeah. Okay. Yeah, I think we're okay with that. So what I can do is that, and this is, if you've gone through and read Appendix E in your textbook, your author talks about this as omega tau goes to 0. This term goes to 0. Okay, and the term is this thing. But as omega tau goes to infinity, as it gets larger, the term, this thing, approaches 20 times the log of omega tau squared. Okay? And let's see, how can I get rid of an omega tau squared? I can say that this is then, what, 40 times the log of omega tau. So we're going to have a steeper slope on that one. Okay. Let's see what this looks like on a log plot. I'm going to start out with this thing here. I'll say that 0 is about here. Make sure I got this right. Yeah, 0. And I want to go from about minus 40. So 1, 2, 3, 4. So that's minus 20. Minus 40. There's 20. There's 40, and as for the logs, yeah, I got it right this time. I'm going to say that this is 1. Well, I guess I could say that this is 0.1, and this is 1, and then we have 10. And 100, and we could even say 1,000 if we wanted to. There we go. Okay. So this is omega. So if we look at this first term, we've got a line. It's going to be at omega is equal to 2. It'll have a value of 0. So let's see, where's 2 on this thing? There's 1, here's 2. So it'll have a value of 0. And then we had this other point when omega is equal to 20, it has a value of 20. So here's 10, there's 20, so it'll take on a value of 20. And let's see, if we are at 200, we should be up here at 40, right?
Is 20 log 100
40?
Were you just following the trend?
I was just following the trend. But I think yes on the other one. Try and draw this. Okay, so I've got something like this. This is 20 log of 0.5 j omega. Guess I should have done it with a dotted line. Well, I'll come back and use a bold when we put them all together. So then the next one is fairly straightforward. We have 0, and then it's going to turn down at a half, isn't it? So at a half, that would be 0.5. There's 0.2, 0.3, 0.4, 0.5. So we're going to go 0, and then it turns down. So at 5, there's 5. We should be at 20, down 20. And then at 50, should be down 40. So we got that one. So that one's done, and that one's done. Now we have this last one. So it's got a center at 0.1. Okay. Let's see. That's tau. So where's the corner on that going to be? Center is 0.1. The corner is at omega t, right? Because where's that go to 1? Omega tau. So that should be 10, right? Yeah. Okay, so at 10, we'll come over here. So it's going to be 0 up to 10. And then it's going to turn down. And it turns down at 40 decibels per decade, right? So if I'm at 10 at 0, and I go 40, it's turning down at 40 decibels per decade because it was a squared term. So I've got to be at 100, I better be at minus 40. So I'll do something like this. Where the corner was 10?
Yeah.
Because tau is equal to 0.1, and the term then the log term goes to 0 if omega is equal to 10. Okay. So what we can do here is, let me start to put this together. So at any of these points, I'm going to start to add this up. I'm going to have 0 plus this. So the actual curve is going to follow along this for a while, isn't it? Until we get up to there. And then what's it going to do? Start to level off, won't it? And it better level off, if this is 0 and 0 and this, it better level off like that. Okay. And then what's it going to do? This is where it gets a little bit tricky, and we have to come back and use the zeta term. I come over. And then if you look at, and the author's got a good figure, the with zeta equal to, what do we have, 0.2. Depending on what zeta is, like I said, your author has a good figure in the textbook. You add this little knot to the curve, depending on what that figure is for different values of zeta. And your author in Appendix E has a good table of that. So we're going to end up with something that goes up just shy of getting back to 0 and then starts to follow this back down.
And it'll follow the negative 40 decibels per decibel.
To some extent. I mean, it's still, you've still got contributions by this one and that one, but the yeah. So yes, you're right. So it should be following that one. It should be a little bit. So you have something like that. So I mainly show this so you know where this came from. When you start to have to mess around with this and look at the tables, I'm not sure that this straight line approximation has a lot of value. It's probably a lot easier just to turn it over to a computer at that point. But I wanted to go through this. Your laboratory has a complex. I don't remember whether it's a pole or a zero. So you'll go through this process with the laboratory. And your author does a pretty good job of explaining this, like I say, in Appendix E of the textbook. Questions with that? Well, I actually have on the website, I have some plots of this. Let's see, page 3. So this probably does it show up? Oh, I guess it's okay. You can kind of see where it is. Probably can't read it. But if you look at, there's these sub folders down at the bottom, sub pages, the Fourier demos, the free mat with Bode plot. There's the Matlab Bode plot. So we're going to be looking at the free mat Bode or the Matlab with control. So that'd be the control toolbox, which makes this really easy, or the Matlab without control. And the Matlab without control is very much like the free mat. Okay, if you have the control toolbox, then you'll see it's quite a bit different. So I don't want to go through this, to spend too much time on this, but just kind of point out some things that's here, and you can go and look at those on your own time. So if we go here, this is actually free mat. Okay, and you can see that we set this up. Here's your transfer function right here. And there's nothing particularly sacred about this. There's 20 times the log of the absolute value of the transfer function. And what are we plotting it against? We're plotting it against omega. So that's really what that is. I mean, there's nothing these are things that this would have been a pretty decent final question in what, GE 102. Just using a semi-log plot. We're using a semi-log plot. And when you get through that, should come up with something like this. And we didn't talk too much about the phase angle, but the magnitude looks a little like what we've seen in the past. You could do that pretty easy with a straight line approximation. The next one is, this is Matlab. So I take this, I believe it's the same transfer function. Let me double check on that. Yeah, with the same values. So everything's the same. There is one thing as far as the phase plot. If you have it jumping around at minus 180 and 180, Matlab has this neat unwrap command that can help you with that. FreeMat, you get what you pay for. You don't have that command. So that's why this is Matlab. The FreeMat one didn't have that. It's probably not necessary in this one. You get what, exactly the same thing, don't you? There's that. Yes, looks like very much the same thing. So if you don't have Matlab, download FreeMat. You can do good work with FreeMat. Now, if you really want to make life easy, what you want is, this is a Matlab with the control. Okay. So remember, we had this. We had Matlab without the control. Then we had the FreeMat. Those are about the same. You've seen that. Now, Matlab with control. That's significantly different. Basically, all I do is I give the problem in terms of a polynomial. Okay. So I've got a polynomial here and a polynomial there, defined in terms of j omega and the constant. And then the Bode plot, you just have the numerator and the denominator. So a lot easier than what you've seen. And here's the results that you get here with that. So you get a nice Bode diagram out of that. So if you're going to do a lot of this, get something that's got that control toolbox. If you have the student edition of Matlab, you actually have that control toolbox, so you can play around with it. If you go to the lab here, it has the control toolbox. So something to play around with. What do we have here? This was, I think this is homework problem number 1, I think. Yeah. So that's one of your homework problems. The idea with the homework problem is to do it by hand, but a good way to check out your work by hand is to see how it works with Matlab. So it looks like I'm using the unwrap command, so I was using Matlab and not FreeMat. And I have my transfer function right there. And hopefully you come up with a hand solution that looks something like this. Anyway, you thinking about the homework? We didn't do a lot of homework in digital, but starting to look at the homework hopefully now as we go through this. Well, that's it for Bode plots. We're running about a lecture ahead. I think next week we would start Fourier series. So I wanted to just see if we could trudge ahead and get into Fourier, since we've got quite a bit of time left in this lecture. And the way I'll do that is go back and pick up where we left off on that last term. We talked a little bit about that last term, and we're going to go into a lot more detail. Okay, so again, we're switching gears rather significantly from our Bode plots to Fourier. I think we talked a little bit about the history of this last term when we were doing this. Developed by Jean-Baptiste Joseph Fourier for his work in heat transfer. So he was working more in the mechanical area at that time. Usually we see this in electrical, although it can be applied to any periodic function. And what can be applied to any periodic function is we can represent any periodic function with this expression, that f of t is equal to some average value plus the sum from n equals 1 up to infinity of a sub n times the cosine of n omega naught t plus b sub n times the sine of n omega naught t. Okay? So we could represent any periodic function. So some examples of periodic functions, I think we talked about these last term, but last term was apparently a long time ago. I mean, you could do this with a sine and a cosine, but it'd be kind of silly to. You would just get back those terms. One that we'll do right off is a ramp wave, something like this. Ones that come up all the time, and we're going to tackle more eventually, is a half rectified wave. Let's say that you're doing some power supply work and you just want a really cheap power supply. You can take a sine wave and you just use one diode and you get a half rectified wave that looks like that. You might use 4 diodes, a diode bridge. You get a little better wave then out of it. It will flip the bottom up, so you get a fully rectified wave like that. And we'll talk about then taking that and trying to clean that up and turn that into a DC. Some people talk about duty cycle or pulse width modulation. Fairly common now in a lot of things. Let's say that we want to take a DC signal and we want to have some variable speeds. Like in your car, you want to control the fan speed on the heater, or maybe you want to dim the lights in the dash. What we do is we just turn it on for a while and then we'll turn it off. And then we'll turn it on for a while and then turn it back off, and essentially manufacture a signal like that. And if you want the old fan to go faster, or you want the lights to be brighter, what do? Leave it on for longer, right? And then leave it off for a shorter period of time. So we'd have something like that. If you look at the dimmer in your house, you know, maybe a dimmer, a light dimmer in the living room or something, you might think, well, you could just drop some of the voltage across a rheostat or potentiometer. That's probably going to set the wall on fire. Because if you think about it, if you got a 100-watt light fixture and you want it to dim 50%, how much power are you going to have to dump in the wall at the switch? 50 watts. Okay, so this is a thought experiment. Don't try this at home. Take a 50-watt light bulb and shove it into the wall. Okay, all packed with insulation. What's it going to do? What's that? Combust? Yeah. Okay. Yeah. So that's why you don't want to do that one. So the way your light dimmer works is it looks at this thing and says, well, I'm going to turn on here, and then off, and then I'll turn on again, and I'll be on there, and then I'll turn off, and then I'll be on again. So you get something that looks like this. Okay, which is definitely a periodic symbol you can deal with. And we're going to be doing some fairly computational labs, and I'll bring a demo in of this. I've got just a plain old light dimmer, and we'll hook an oscilloscope to it, and it's kind of interesting. You see that very vividly there. This is really a big area in motor control. If we think about taking an AC motor, and when you turn an AC motor on, it's just full on, and when it's off, it's full off, which can be kind of hard on mechanical components. So really in the last probably 25 years, motor controls really come online, where we'll start to ramp up the motor speed. We can control the signal into it. We can control the frequency. So we'll start out with a nice soft start. We don't have to then have as robust of mechanical components that thing drives. The reason that we haven't been doing this for too long is, well, we've been doing it with some using DC drives and things like that, but using AC, we haven't been doing it for too long because it wasn't until recently that we had a computer that could compute fast enough. I mean, if we look at a 60 hertz signal, how much time do you have in here? About 16 milliseconds? Okay, so you got to do some pretty significant calculations in 16 milliseconds to pull this thing off. So that's not a problem now with computers, but a few years ago, or many years ago, it was. So those are some periodic signals that we can definitely use this on. And like I said, oftentimes this F of t we will replace with V of t or I of t, although it could be temperature, could be a stock price, anything that's periodic. A few definitions that we should probably talk about. We could talk about n equals 1, 2, 3, and so on. These are the harmonics. So when we talk about 2 omega naught and 3 omega naught and 4 omega naught, those are our harmonics terms. If we look at the fundamental frequency, the fundamental frequency is just going to be based on omega naught, which, remember, that's equal to 2 pi times f naught, or it would be equal to 2 pi divided by the period. Most of our work in here will be in calculating the A sub v, the average value, and then A sub n and B sub n. So maybe we better talk about some rules. So some conditions for the use of this. F of t has to be single valued. So let's see. An example of something that isn't single valued. Most real generators are not going to produce something that's not single valued. I think that's impossible. But let's say that you get something like this. Okay, is that single valued? Certainly not. Okay, so we can't have that. You might say, well, I've seen a sawtooth wave. Well, if you look at a sawtooth wave, a proper sawtooth wave, usually when you look at this thing, it does something like this. Okay, so you see the difference between those. The other thing, f of t as there's a finite number of discontinuities or minimums or maximums in one period. Okay, and remember that's one period. You might think, well, any one of these, if you consider this going on for from negative infinity to positive infinity, you could have a problem here. But if you look at just one period, it's not a problem. I'm not even sure I can come up with a good example of one that defies that. The last thing is to calculate these values. You got to make sure that the integral exists. So the integral from t naught to t naught plus t over the period of the absolute value of f of t dt has to exist. Okay, so we'll stick with ones that we can integrate. So those are the requirements. I think we talked about those last term, but reiterate those. Well, let's look at those coefficients then. How do I calculate a sub v? A sub v, that's the average value. And we can say that that's 1 over the period t times the integral from t naught to t naught plus t of f of t dt. So hopefully you can integrate the thing. Then we need to talk about a sub n, which we could say was, sometimes you give it the symbol a sub n, sometimes a sub k. We can say is 2 over t times the integral from, depending on whose book you're reading, whether it's a sub n or a sub k, t naught to t naught plus t of f of t cosine of, whether it's n or k, maybe I'll stick with n, cosine n omega naught t dt. Okay, so usually we just write it like this, but that's where the parentheses would be. Okay. And likewise, if we have b sub n, or some authors talk about b sub k, that would be 2 over t times the integral from t naught to t naught plus t of f of t. And we have sine of n omega naught t dt. And again, we usually write it like that, but for this time, the parentheses would be there. So you can see we're going to do quite a bit of integration when we go through this. The first example in here will be the same one that we did last term. We're just going to hit it straight up and do it. I don't think it's got any symmetry anyway, but normally we'll try and look for some symmetry, because with some symmetry we can avoid some of this integration and make our life a little bit easier. Questions with that? The one thing that I should probably go back and mention on this page here, this infinity, this is for it to equal. If you go to infinity, it's equal. No question about that. Okay. As a student, I was always a little concerned about infinity. I didn't have time to wait around for this, so how far do you have to go for it to be pretty good? Well, you can start to get things that you'll recognize maybe with 3 or 30 or 300. Okay, you pick whatever numbers you want. 3 you can do by hand, right? 30 you could probably do by hand if you really had to. 300 would be kind of miserable, but start to get into the area, you could do 3,000 real easy with the computer, right? Okay, so you don't, suffice to say, you don't have to go out very far. I think we did an example of this in GE 103 last year, gave you something good to calculate. In this range, you could actually see the curve. It's going to be a little bit ugly, have a little bit of noise. In this region here, you're probably not going to graphically on the screen be able to tell the curve from what you think it is. So it's a pretty good technique. Well, we've got these down. Let's go ahead and apply this to a problem. So I'm going to start out with a ramp. So we're going to say we have something like this. It comes up, it drops down, up again, down, and so on. And I guess it was doing that since the beginning. And that goes to some value Vm. And we could say that that's 1 period, that's 2 periods, there's, of course, 3 periods, and so on. And we like to come up with a Fourier series representation for this. We would like to say that v as a function of time is equal to something. We'd like to have a Fourier representation of that. Well, you could actually go wherever you want. I mean, you could say that I'm going to start right here, and I'm going to go one period, and I'm going to go there. That's probably not the easiest period to look at. Okay, I think I'm going to take t naught right here, and take this as my t naught plus t. I think life will be a little easier with that. So if I look at the curve there, I could say that v of t is equal to, what's the rise on this thing? Vm divided by the run, t, and multiply it by t and add 0 to it, right? This is a classic equation, y is equal to mx plus b, right? It's the equation of a straight line. So I've got then that v of t is equal to Vm over t times the time t, where capital T is the period and lowercase t is the time. So now I put these into effect, right? First one, I better come up with the average value. So let's see how that works. Average value is equal to 1 over t times the integral. We're going to go from 0, because t naught is 0, to t naught plus t. That would be just t then, of Vm over t times t dt. So we could say that this is equal to, Vm should be constant, t should be constant. So I'm going to have 1 over t times Vm over t times the integral from 0 to t of t dt, right? Which turns out, when you get done with this, to be equal to 1/2 Vm, and all the dust clears. Does that seem like the average value? Yeah, I mean, I think if you were pressed and you had to find the average between those two points, it'd be 1/2 Vm. So that makes sense. Probably could have just written that down from the get-go, but it's good practice. The other two are going to be tougher. So let's get started with a sub n or a sub k. So we can say that a sub k, maybe I'll do a sub k. I think that's consistent with your author. A sub k is 2 over t times the integral from 0 to t of Vm over t times t times the cosine of n or k, we'll say k, omega naught t dt. Okay. So let's see, you say this is going to be equal to 2 Vm divided by t squared, and then I've got the integral from 0 to t of t times the cosine of k omega naught t dt. So you put that in a computer algebra system. You could do integration by parts. You could look it up in a table. If you go to a table, what are we looking for? The integral of what? X times the cosine of ax dx, something like that. Okay, and when you do that, and you can choose how you want to do it. Tables is as good a way as any. But when you do that, you're going to come up with this, 2 Vm over t squared. And then we're going to have the terms here. 1 over k squared, omega naught squared, cosine k omega naught t plus t divided by k omega naught times the sine of k omega naught t evaluated at 0 and t. It's going to get worse before it gets better. So we have k squared omega naught squared cosine k omega naught. What's omega naught? Omega naught would be equal to 2 pi times f naught, which we said was also 2 pi divided by t, wasn't it? Okay, so I have, let's see, and I could make the substitution there, but maybe some of these will cancel out. I won't have to worry about that, so let's not get hasty about that. I'll make my substitution here, 2 pi, and then I will have t. So that's my omega naught, and then when I put the upper limit in here, I get t there, plus t over k omega naught sine of k 2 pi over t times t, and then what am I going to have? Minus, because I got to do the lower limit, cosine of 0, right? When you put 0 in there, you should get 0. And then I will have minus 0, because you put the 0 in there, you get the 0. So I get to cancel this, and this turns out to be equal to the cosine of k times 2 pi. What's that?
Where did our t go?
Right here?
In the cosine.
And the cosine. Oh, right here?
Yeah.
I put t in, right there.
Oh.
Capital T. Very good. Same thing here. In the lower, I get to put 0 in. So let's see. If I look at the unit circle here, cosine of k times 2 times pi. What's that turn out to be? Let's see, when k is equal to 1, what do I get? 2 pi. So 2 pi is right there. What's the cosine of that? 1. Okay. When k is equal to 3, I get 6 pi. I'm back here. I'm always at this point, right? Okay. So this term is always 1. So I can say that I have 2 Vm divided by t squared. Looks like this is always 1, so I have 1 over k squared omega naught squared.
Can you have half numbers as k?
No, but sometimes k will be odd terms or even terms. That's why I'm always a little more careful with not trying to. I go to the unit circle so I don't jump to conclusions. But yeah, k is always going to be integers. It's the it comes from this thing right here with the n or the k. So it'll be 1, 2, 3, and so on. When we get into some symmetry, we'll see that sometimes it's even or odd. But for now, we're just taking it as integers, positive integers. So we got 1. Let's see, if I cancel this out, I have the sine of k times 2 pi, which is what? Always the same point. And that's always 0, isn't it? Okay. So plus 0. Then minus, what's cosine of 0? Yeah, that's 1, isn't it? So I'm going to have a, is that right? Yeah, so I've got 1. I thought I had a second negative sign in there, but I'm good. So minus k squared omega naught squared. And then I won't have to worry about that 0. So I get something in there. So if I have this and I subtract that, this whole thing turns out to be equal to 0, doesn't it? Yeah. So that is our a sub k. So we've got a sub k is equal to 0, and we've got the average value 1/2 Vm. Yes?
So in the first part, you have cosine of k times 2 pi.
Right here?
Yeah, right below it.
Here? Okay.
Isn't cosine 2 pi negative 1? Or no?
Yeah. I think I'm always here on the unit circle, right? Yeah, you'll see me draw the unit circle on this just to make sure we're getting our thinking clear. I think we're okay there. So we got this one, we got this one. Hopefully b sub k turns out to be something other than 0, or this is going to be very boring, or maybe I should say more boring than it is. So hopefully it's not too boring. But, 15. Okay, so what do we have for b sub k, or b sub n? We can say that b sub k is equal to 2 over t times the integral. I'm going to go from 0 to t, v sub m over t times the sine of k, I'm doing k, yep, omega naught t dt. So that's b sub k. So we've got that this would be equal to 2 Vm divided by t squared times the integral 0 to t of t sine k omega naught t dt, where I'd go and look for the form. If I was using math tables, I'd look for the integral of x sine a x dx, something like that, where a is a constant. And you'd come up with something like this. It'd look an awful lot like, not exactly, but very similar to what we just did for cosine. And then we have a minus here, so that's one difference. So we have sine, this will then be cosine. Yeah. So then I just plug in the values, the limits. This is going to be what? Sine of k, when I make my substitution around omega naught, is 2 pi over t, and then t will become t, so you're going to end up with what? Sine of k 2 pi, and we have minus t over k omega naught cosine of k 2 pi, and then we've got to subtract off the lower limit, so minus 1 over k squared omega naught squared sine of 0, and then a negative and a negative become a positive. I guess it's kind of a mute issue. You get 0. So let's see. Again, I'll use my unit circle, try and make sure I don't make mistakes on this. It's a shame to get through the really tough part here and then make mistakes plugging these things in. So what's the sine of 0? That's 0, isn't it? Okay. And then if k is taking on the values of 1, 2, 3, and so on, if I'm looking at 2 pi, k times 2 pi, I'm always right back there, aren't I? So the cosine of that is what? Cosine is 1 And how about the sine? That's 0, isn't it? So it looks like I'm left with, for b sub k, left with 2 Vm divided by t squared times 1 over k squared omega naught squared times, whoops, I don't square those, do I? This goes to 0. This is the only term that I'm going to have. So, okay. And I better have a minus, I'll have a t in there and a minus 1 for that negative sign, right? Do I have everything now? Yes. Okay, so what's this going to be equal to? 2 Vm t squared with the negative sign out front. Put a t here for that. We got a k. We got omega naught, which is 2 pi. Denominator of a denominator becomes a numerator, so I have a t, right? So I get to cancel those with that. I get to cancel that with that. And I'm left with b sub k being equal to minus Vm divided by k pi. So we're going to put this all together. We put it together where? I have to go way back here. Right into here. So I'm going to put it together into that expression. We got our average value, we got our a sub n or a sub k, we've got our b sub n or b sub k. So let's see what that looks like. So we could say then that v of t is equal to the average value. What was our average value? 1/2 Vm, thank you. So 1/2 Vm, and then I add that to the sum, n equals 1, 2, 3, and so on up to infinity of a sub n. What was a sub n? Yeah, 0. So I'm going to have 0 times the cosine of n omega naught t. And a lot of times at this point, even people that use k will start talking about n's for some reason. Plus, then we're going to have b sub. So I have this minus Vm divided by k times pi times the sine of n omega naught t. So we can tidy this thing up. What's that going to look like? Vm over 2. And then I'll subtract off. I think I can factor, this one goes away because it's 0, right? I can factor this one out. Vm is a constant. I can bring that out. Pi is a constant. And then I will have the sum through infinity. If I've taken out the negative, the Vm, and the pi, I will have 1 over, and I shouldn't have written the k. This should really be n. So I'll have 1 over n times the sine of n omega naught t. Should at least be consistent. So that's one way to write it, and perfectly fine. If you wanted to start looking at the terms, you could show this as Vm over 2 minus, what would we have? Vm times the sine of n omega naught t divided by n pi, n being 1, so I'd have pi. I guess if n is 1, I can just take this out. And then I'd have minus, let's see, if n goes to 2, what do I have? Minus Vm sine 2 omega naught t divided by 2 pi. And then subtract Vm sine 3 omega naught t over 3 pi. And it just goes on from there. Questions with that so far? Well, there's some resources on the website for you. Again, if you go to the under the transfer functions, oddly enough, the ones with the Fourier demos, that may probably be more helpful for the laboratory when we get into doing the laboratories number 4 and 5, I believe. But what I'm going to show you today, you'll find under the transfer functions subpage. So here I set this up, and I'm looking at the first 3 harmonics, okay, which should be near and dear to us because we actually did the first 3 terms. We've got this, 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 and that. So there's the average in the first 3 harmonics. So I go through that, and you get your output look something like this. There's the average, and here is n equals 1, and then this is n equals 2, lower frequency, and then higher frequency yet, n equals 3. So we're going to start to add those all together. That is, you can imagine drawing a line through here, and you're going to add those all together. And when you do that, there's a slightly different program in there that gives you the sum of these. So I've got a loop going here where I do this sum. This is in Matlab. And I think this would work just as well in FreeMat. I don't see anything that wouldn't work in FreeMat. It looks like my maximum n value is 1,000. So we're going 1, 2, 3, and so on to 1,000. So it should look pretty good. And when we get done with it, it does look pretty good. So here we are. Started there at 0. Took our magnitude of 1. This is n is equal to 1,000. So you'd have a hard time distinguishing that from the real ramp. 1,000 is still a far cry from infinity, so it's a pretty good technique. So what we'll do going forward is we're going to look at ways to try and streamline this process. If we have symmetry, odd function symmetry, even function symmetry, we can make life easier and quicker in calculating those coefficients. And then we'll start talking about, well, what happens if we take this signal and it has high frequency terms and low frequency terms, and we start to shove all of those terms into this filter. And if the filter doesn't let the low frequency terms through, what are we going to get out? So that's where we'll take this. Once we get comfortable with just doing Fourier analysis for the sake of Fourier analysis, we'll start to go this way, start to feed it into a filter and see what you get on the output. It should be kind of interesting. If you take something like this and you pull off all of the low frequency terms, or you pull off all of the high frequency terms and see what you get. So that's where we're going in the days and weeks to come. Take care. Yes?
Another question that might apply, well, people in class. On Monday, the 18th, or on May the 18th,